thank you for inviting me, and thank you for your interest about crocheting and mathematics and so well. And I decided I'll just tell you my story, how it is that you study mathematics and then suddenly become artist totally unexpectedly. So, okay. Well, it all started in Riga. Actually, so my first school wasn't in First Gymnasium, but I was like most of my schooling was in this school. And if you ever in Riga, this is near the Freedom Monument, sort of like facing Freedom Monument. It's on the left side, and so that's a school. It's just the best gymnasium and always has been, with a specialization in mathematics and physics. And so I graduated, and I was like a school. We did have some art classes, and honestly, all I learned to do as an art class was that once we had a substitute teacher from Academy of Arts, and he took a white egg, put on a white paper, and said, "Draw it." So that was my art education, because like for everything else I did, that the teacher said, "Well, you can do anything else, but not the art. Well, there's nothing from you will ever be anything like an artist." So I grew up and went to study mathematics, which is, if you face Freedom Monument, like the next block on the right. And at that time, the mathematics faculty was in this old building of university. And actually, I lived like 2 blocks from there. So it's just, like felt like home. And so this is what I studied. And then specialization in mathematics in those times, as you see, like it's way before you were born, is so well that you start already on the first course, and I chose to be like study mathematics exactly because I can't be an artist. And well, I never even considered a thing like that. So, and that was like that in University of Latvia, like where I had lots of math courses, and actually I did my graduate work in theoretical computer science, and then I just took then other things, and you never know in your life where your path will lead. And now it's been like 20 years. I'm already like living in Ithaca, New York, and I was teaching in Cornell University, and mostly calculus, as sometimes I'm joking, teaching calculus. I was teaching calculus to earn money to buy yarn to crochet my hyperbolic planes. So that's that thing. But then there is in this Cornell University, it was like 20 years ago now, I was assigned to teach hyperbolic geometry in the fall semester. And that reminded me about like some picture I had as an undergraduate when I was in the University of Latvia. And that was exactly this picture. So there is a way to say that in Euclidean geometry, which is the top picture, if you are having like a given line, and then you are having a point outside this line, then through you can draw only one parallel line through that point. While in hyperbolic geometry, you can have lines, and they are intersecting, and then they are still parallel to the given line. So for me, that was a great puzzle when I was an undergraduate, and I wanted to understand that. And I was asking, like the instructor, well, how is it? Because I really needed to have this feel. And she just said, like, you have to imagine it. Well, imagine. The geometry at that time was called imaginary geometry, following Lobachevsky's tradition. And imagination is, well, in classical and medieval and early modern philosophies, it was defined, so I should have some notes to see, is as a faculty involved in the production of images of things no longer present. That doesn't give you an answer to the question how to imagine how this can happen. And interesting actually that both Latin term for imagination, which is imaginatio, and also a Greek term, which is phantasia. They both come from the root, which means light, following Aristotle's tradition that without light you can't see. And some early philosophers even said that imagination like for geometrical figures, they are grasped by imagination alone, which is sometimes referred to as an intellect. So that was by Thomas Aquinas, and I didn't know all these philosophical things at the time. Maybe my instructor knew, I don't know. But so thinking that if you have no imagination and no intellect, it really hurts you, particularly when you have studied mathematics and still don't really understand. But as a student, and I believe you have those cases too, eventually, even without much understanding, eventually you pass the course. Otherwise, I wouldn't be here, of course, and just move on. But now I have this task that I have to teach hyperbolic geometry myself. And then that is like, it's about like what, 20 years later, you know, like, and now those memories come back. And I definitely didn't want my students, when I'm teaching, to have the same bad memories about this subject. So what to do? I went that summer, I went to the geometry workshop, and then I saw, this was like first time I saw the model of hyperbolic plane. So this model still is at home, but this was inspired by William Thurston. So it's glued from the paper strips. You can call those paper strips like annuli, and they all have the same radii, and it's big. It sort of like gives you a no perception, yeah, thing, but you can't really fold it and explore. It's pretty fragile. And yeah, and I later, when I met William Thurston, I actually asked him about the history of this model, and I asked him, did he know that in 1868, Eugenio Beltrami, who was first describing this surface, that he also made a paper model? And Thurston said that he didn't. That first time he made a model is that when he was studying in a small college in Florida, and with his classmates, they wanted to understand exactly the same question I had. What is happening on this surface? And then there is a nice quote, which, so Thurston is several times, he's like really used to stress that to understand was the goal I gave for my high school yearbook. And this is still what drives me. I love to teach, I love to reach understanding first, to see something, big or little, that doesn't make sense or is simply discordant, and then to reflect and ponder, to search and stare in my mind's eye until sometimes miraculously vision is transformed and mist and muddle developing into forms, order, and connection. And then that is really important, that mathematics is not about numbers, equations, computations, or algorithms. It is about understanding. And so, and that's what he said, that's when they made the model. Well, going back, it was that summer, so I see that model, and I was thinking, well, how come? I can't use this really well, you know, showing it, okay, that's how it looks, but I would like to play with it. And I started to think how to do it. Well, and then I often have this question about the aha moment, how did I came up with it? And then the thing is that I realized there is this exponential growth, which is embedded in hyperbolic plane. And then if you draw hyperbolic growth, this is how I first heard about exponential growth when I was like in a school mathematical circles. So it was like some math club. And it was said how rumors spread. And it is like, if I know something and I tell a friend, and, you know, like, so this is a secret, but just only you, I tell that. And then the next day we go out and each of us tell just one more person. Yeah, so if the first day we knew 2 of us, next day it's 4, and so it goes. Yeah, so like that's to the power 2 to the power of x. These days it's easier because after financial crash, I know that when I was teaching calculus, I said, well, you know, it's essentially a Ponzi scheme, and then everybody gets it. Those are all those lotteries and money laundering and everything. Yeah, so well, but then, and then I thought like, okay, if I draw this exponential growth like this, and then that aha moment was, If I look at this graph, it looks like crochet picture. So it means I can crochet. Well, what happens if you crochet, meaning like doing adding a stitch in each stitch? So then eventually it's a hyperbolic, like this exponential growth happens very, very quickly. And so this is an example. Yeah, so this is an example. It's very quickly starts filling. It's like adding every stitch. So this would be like 2 to the x. Well, so this is, I understood that's like too much. I did it a little bit less. And this is my first crochet plane. This is like crocheting 2 and adding into the 3rd stitch. If I would want to describe how the number of stitches grow, that would be 3/2 to the x. See that the growth is slowed down. And and then I realized, okay, so there is a thing. 2 to the x is what I showed you. Yeah, so this would be like adding a stitch and everything. 3/2, so then if I would have a 1 to the x, it means it's just plain. Yeah, nothing changes. Okay, so therefore there should be this ratio between 1 and 2. Yeah, and that does the crochet. And since I wanted to get a picture, so the picture which I showed you was like on a board, and I really wanted to understand that. Well, so I started to experiment with these ratios. Like, for example, when you are getting closer to the 1, like 12/11, yeah, so that would be like just slightly more than 1. So you are getting like more flat, this surface, and now you can start doing the pictures. And then I finally got to the, well, before we go further, what is this hyperbolic plane I'm talking about? Just a little mathematics. We can think about, in ways of tiling, there are several ways we can think about hyperbolic plane. The one thing we can talk about like a tilings, it's like in beehive. We can tile the plane with the hexagons. Now, if we are taking a hexagon out, like we are just, and doing these 5 hexagons around the pentagon, then the surface starts curve, and when the curving finishes, so it closes. Yeah, so it closes, and we are getting like traditional soccer ball. They are now changing these designs for soccer balls, and so well, but essentially that's the same thing also, you know, like. And so this would be like one way to go. And then the other way is, if we, in that same hexagons in the middle, we put not a pentagon, but we are putting a heptagon that is with 7 vertices. So then the surface starts curling away, and so that is a different way. So those are the curvatures. There is a, if it's only tiled with hexagons, that would be 0 curvature. If it's curved like with that pentagon in the middle and we get a soccer ball, that would be a positive curvature. And now this is a negative one, or we can call it hyperbolic soccer ball. So if we wish, of course we can't play. Now imagine if I'm having like a sheet of paper and squish like an orange peel, which would be like there is an orange, but when I squish it, so there is not enough surface to cover that paper. So while if I squish the hyperbolic plane, so that's a crochet version, that is like too much. Yeah, so that is like too much the surface. So there is a difference in the surface area too. It's nothing what I'm talking about is like simply like mathematicians got it out of, you know, like somewhere. That in mathematics trying to describe like various properties and talking about the curvature is the way describing properties of the surfaces. And negative curvature really exists also in the nature, so there are a couple examples, like these nudibranchias or bulbs. After I crocheted first plane, there was also, you know, like we did like a publication in this math journal. But before I go any further, so here it is, like some things which you can see here, and you can later come and see it. Like, so how do we get like a straight lines, and how do I get that picture what I wanted with my hyperbolic plane? So here it is that we can do with these models the same thing as we do with a piece of paper. If we have a piece of paper and want to get like a straight line, the easiest way to get a perfect straight line is just to fold. And once we fold it, well, we get like immediately straight line. So we can do it here too. Now if I'm folding, yeah, so that's the same thing. So this is a straight line. Why it looks, you may say, well, how it's straight, you know, like, because we are looking from outside. If we would be like a tiny ant walking here on this plane, so then we experience this line also. It's totally straight, but it's, and I'm not stretching really. It's just straight. And now if I fold, here it is, I can fold two mutually intersecting lines. But as you see, neither of these orange lines are ever going to cross the white line. So I would encourage you to try and fold and see. So this is a picture, actually, why I wanted really to crochet and experience what happens. And do you see what happens, why they are not intersecting? It really gives an answer. And the answer is that in hyperbolic geometry, if we are having like two lines, they are not intersecting, but so what we want to call a parallel is they are not intersecting. Okay, so they are not intersecting because they are at some place, they are coming closer, but then they are diverging on both sides. They are just getting further and further apart. So they clearly can't really build railway on the hyperbolic plane. Yeah, so those lines would be, doesn't work. Well, so, but this is about, yeah, we can ask, well, oh yes, well, there is another mathematical question which will show you that, you know, like in school you're all taught that in Euclidean plane we are having a triangles and the angle sum is, so what's the angle sum, interior angle sum in triangles, what it is in Finland? You are having any triangle and then you adapt. No, well, you know, these days you don't know. Maybe in different countries it's different. So what's in Finland?
I think it's 180.
180, yeah? Oh, okay. So yeah, it's a European Union, I guess. Yeah, so good. So in some places in America, they also say 180. Yes, so well, so yes. But then when you are having, so yes, okay, so let's agree that's 180, I like it. So then if we are having a sphere, so what happens with a spherical triangle? Even if you've never had a spherical geometry. Now, imagine that you are having an apple and you are just cutting out 1/8, yeah? So you can cut in half and then you can cut half and another one. So can you imagine what are the angles are? Yeah, so those are 3 right angles. Yeah, it's 270. And, well, there are ways you can see, but anyway, so the fact is that on sphere, if you are having a triangle, that the sum of interior angles will always be more than 180 degrees. While, of course, we need like counterexample. Yeah, if we have 180 degrees on a plane, sphere is more, so then what happens on hyperbolic plane? Now you know what it is. It's less, yes, it's always less. And there are some nice cases that, and that's you can also see, and that's put on these models. Yeah, we can just experience kind of like visualize what happens. You can get like the interior angle sum goes to 0. Yeah, it becomes very, very small. Yeah, very, very, very small. At the same time, there is a triangle. And then this triangle is, actually it has name in hyperbolic plane, it's called ideal triangle. And ideal because this is the largest triangle you can have. It's a triangle with the largest area you can have on this plane. So that's why it's called ideal. So we usually in hyperbolic geometry it was said that, okay, well, let's see that this that the area of this ideal triangle is pi, and then we started like think that, but the hyperbolic planes, they are having like playing with these models, they are having a radii. And it was assumed that all the radii of the hyperbolic planes are 1. But we can't talk about all spheres having the radius 1, because not all spheres are, like there is a small sphere and bigger sphere and huge sphere. So how can we say that that's the same radius? And so it appears like these hyperbolic planes, they also have a radius, and we should take that radius in account. And if we take the radius in account, then the correct formula for this ideal triangle is pi r squared. So sounds familiar. Yes, so that's an area for this triangle. So this is essentially what we wrote in a joint paper with my husband and published in Mathematical Intelligencer. And then there was a discussion with the editor because they said, well, how it can be? We are publishing this is a mathematical journal, and we are publishing like a crochet, and it will be on a. So how does it look? And that we convinced him, and since there was this result about this area of the triangle, and we convinced him that this is, it will be okay, and this crocheting is really good for thinking of mathematics, and he didn't really believe us, but published. It got some attitude, and it got some attention. And then there was this, the writer Brooks from New Scientist. He wanted to write in a Christmas journal. He wanted to write about this crochet. So what he did is he wrote an email to my husband. We had a joint paper. He wrote an email to my husband with a question: how did he crocheted hyperbolic plane? So my husband was laughing. He said, oh, it's kind of like a funny. Yeah, so I said, well, you know what? I understand that in America, they think that women can't think mathematics, that they don't have any brain. But taking away even crochet skills from me as a causer, that's kind of too much. So, he suggested that he reads more properly paper because it was written who crocheted, and I said, well, but anyway, so he cleared it up. So what I did is I really don't have this most unique hyperbolic plane with me, but I did give him a little bit of a yarn. I gave him a crochet hook and said, since you are getting these emails, how to crochet hyperbolic plane, and you have published a paper, you should at least do one. So he made one this big. So now it's... Well, after that one, we actually wrote 2 books. We wrote Experiencing Geometry, rewrote, and where I kind of crocheted illustrations. And this book got translated also in Japanese. In a classroom, when I was teaching, so the students are not required to crochet, but they can use these models. And as you see, we have balls and everything in a classroom. So it was some time ago. And so then there was an interview. After we gave a public lecture about these hyperbolic planes, then appeared the interview in this magazine, and it was kind of like a crucial thing. It became popular. And when you search for hyperbolic plane, you often see this picture, because that was illustration for this first interview. And that's a kind of And soon after that, after the interview appeared, I got a phone call, and that was from Washington, D.C., in some March 2005. And the woman said, well, she's a curator of the gallery, and would I mind to present my works for exhibit? Because she was getting together works, not the knitting, sculptural knitting and crochet, as you see. And I said yes, and then after I finished, I said, what did I do now? It's an art exhibit. It's in Washington. It's actually on a Pennsylvania Avenue. That's the one which goes from Capitol to the White House. And so, and all I had at that time were models like these, which I used in a classroom. And I said, but I can't send those ones to the art exhibit. So I went to the yarn store, I bought a yarn and started to crochet. So this is one of the very first ones, and so I kind of liked the colors, and it looked a little bit better. So this is also from those first ones, yeah. So then just trying something else, and I did this one, and then this one was more interesting. These were like these three different colors, and by the way, since it's each of them is one skein, so then this is kind of like a 7 shades, but it's one skein. It's about like, I didn't really check the length of it, but essentially that middle area is the same as that like light area around the edge, yeah, because that's the way how it was crocheted. So I submitted the works and sent them to the Washington, and then comes like the opening, and I decided like, nobody really knew me. I went to the exhibit to see the thing, and I walked in. It was a beautiful exhibit. But like I had a feeling, what am I doing here? I was told in school, I can't be an artist. So, like, no, I feel too ashamed. This is like, I know how people, just I had the students who were usually afraid of math and said, oh, no, I can't do math. Well, I can't do art. What am I doing in art exhibit? So yeah, I really had the feeling. Well, finally, I overcame and went to the opening, because I had to meet a friend with whom I was staying at night, and she said she's coming, so I had to go. I wasn't going to do anything else. So, well, and then I got and then immediately from that exhibition I got an invitation to the next one, and which was in American Center for Physics, and that's when I decided that I'm going to do some experiment with colors, since I was doing the previous one. I thought, let's measure. And then for this piece, I really measured each of these. There are four these shades, and each of them is 100 meters long. And then I crocheted. So it means that that's all the dark one. It's the same area as the one which is the lightest one, which is the edge. And that really shows, it was a surprise for me. That's one of the first things. Yeah? So it really shows how we can't really trust our intuition, yeah, because it kind of like felt really stunning how these areas can be the same, but they are, yeah, just from the way how they are made. So they are the same. Well, so that idea, the same idea, playing with the colors, is also in these two works, which was for another exhibition, and which I called "We Are the Same," and it was like really accepted the way, yes, it's. So kind of like every time there appeared, like I was getting like these invitations going to these artists and this mass counts. That was a very high level exhibition. And that is something where I was like invited also to go to the panel, and I would be in a panel with Bernard Venet. He is a very famous French sculptor who also does paintings. He paints equations. And we were on this panel to talk about why he wants to paint equations, and so, and why I'm crocheting these hyperbolic planes. And this, so the panel went well, but then after our discussion, we were invited for a dinner, and we sit next, and he says, oh, you are doing these pieces, you should do something big, like make it big. Yours they are small, they are too small. Well, they were small also, that, that amount of the wool going into them was quite pricey. But you have to make something big. Well, so this was the one which I did for a long time, actually. I never counted how, well, I still didn't do the multiplication, how much I spent on this. Because I had a craft store, about 15-minute walk there. Like I went to the craft store. First I bought 6 skeins, one color, and 6 skeins the other color, and I started to crochet. So just changing, like crochet 1 skeins and change colors and crochet the next one. And I was expecting that this would be like total mess at the end, kind of like makes just colors mixing. No, they are kind of like split. And this was the first time I had the easy time it's hard for me always to find what are the titles for my works, but this one was easy. This was like I said, okay, this is a day and night in hyperbolic plane. And then when I finished with my first 12 skeins, then I walked again, bought a couple more of each color. So I continued until that box was empty. So this was what first one. And then I did another one. So this one, I don't like pink. Trust me, I really don't like pink. It's not my favorite color. It's okay, but not my. But I made like my largest piece I have ever made, and it is from a pink. And that pink because, so I just found this yarn in a dollar store, so it was like the cheapest, and I just like bought everything. And so this was another experiment. Like I was just like doing further experiments. So this is doing from a big piece from the Manila rope, and that one I did with my hand. Then when I was like doing crocheting, but not with a hook because it's really very rough. So I did this one with a hand, and that cost me a little bit losing my skin because it was quite rough. But then I could put it like these together, and I was calling these ones sort of like a global warming warning. Yeah, so it was and then so this is how it went to the exhibit on Design Museum in Milan. I have this exhibit, and so the funny thing is that there you see the guy on the left side with like this red tie. So that he was put there because like everybody usually wants to touch it. And there are things I said like it's okay to touch it. But since it's Design Museum and openings, I didn't want people like to touch something, like they were feeling responsible. And then he was standing there all the time like in Italian, don't touch, don't touch, don't touch, don't touch, like that all the way. And then you see, and then when it already that evening slowed down, there were less people, and and I had gone to see some other works and talk to the people. My husband still stayed there, and he said that he was, like all the time, he was standing there very tight, and just very thoughtful, like looking, don't touch. And he says, and then I see that he stands there, and then his arm goes like this, and then he touches the piece. So also he wanted to touch. Yes. So then there are some other works from exhibits, and then there was there are interesting things. I was like on the left side, there is a piece which I made that American Association for Science wanted to have one of my pieces, but they said, but you have to make it flat. I said, well, I can't make it flat because it's three-dimensional. So I made it as flat as I could. And since it's from American science, and I made like these some mathematical sort of like, you see these yarns, pictures on and everything. And when they saw it, they said, no, we don't take it. It looks too mathematical. Well, that's another part. You never know. And then, as you see, those are the pieces which actually, that's one of my most exhibited pieces, because when art galleries want it, for them it's not too mathematical. For science, it was too mathematical. Go figure. And so now I found on eBay, I was just like thinking, okay, if I'm making things big, so I'll make it even bigger. I found on eBay 38 more, as a previous one was 88 skeins, this is 38 skeins added to that, and so, and it made it bigger. And to my surprise, I got a call from Guinness Record Book in 2000, now I think it was 14, I guess, I forgot already which year, but they called, well, we believe that yours is the biggest crocheted hyperbolic plane. I said, well, I do believe too, I never heard anybody else to be so crazy. And so they said, okay, can we publish? Can you send me a picture? Yeah, so, well, this is a picture in Guinness Record Book. So, and when I'm, so I know you are too grown up, but I know that once I was just like in elementary school and we were playing with these planes, and the teacher told them that I have a piece in Guinness Record Book. Then after I finished my talk, like a little boy comes to me, looks up to me, can I touch you? So this is another piece, like Land and the Sea. So it was like made for student project. There was like Latvians were doing with the schools. So this one is like similar to one which is We Are the Same. This is kind of like worked out in Latvian color, like really from the Latvian flag. And this is in the U.S. Embassy in Riga, so the State Department things. And well, from not being an artist, I got a piece which is in Cooper Hewitt Design Museum. So that was like, so therefore you really never know. And then there is this Lorentz manifold, which is one of the things which will, when we told the mathematical intelligent editors that somebody else will use the technique. So that actually, that's 3 years later, 4 years later, there was another crochet piece in Mathematical Intelligencer, and that was by Hinke and Berndt, that Hinke said, yes, well, they wanted to explain about this House paradox, which creates Lorentz manifold, and couldn't explain students how it looked like. And then she said, oh, and I remember that you were crocheting. And then they calculated by the computer this number of stitches needed, and then put the support in, and they said like, and that's when they created this Lorentz manifold, crocheted. And this is when they were visiting Cornell, so then we got this picture together. So I have done some other manifolds, because it's kind of like a boring making all these pieces all the time. So I started to fold them in various ways. And originally they are all the same, but then when you are like, you can start folding, and I think that's a beauty when you make them, and then you can fold them according to your so kind of like whatever you think that morning or whatever. So it's and so they go. So then in 2012, like I made a figure 8 knot. That was a thing which Bill Thurston we were like colleagues, and sometimes, we talked, and I said, oh, well, what should I do? And he had like some paper model, and he gave me, and he said, well, can you figure out how to crochet this? And I crocheted that, and well, I couldn't figure out, honestly. I couldn't figure out it immediately. And by the way, this is a smaller piece of that. This is it. Yeah, so that's also the one. But that is the one which I was thinking how to make it, and then finally when I did it, I took a picture, and the picture didn't came out well. I said, oh, okay, I will retake a picture, and unfortunately, 3 days later, Bill Thurston passed away because he had a cancer, and he passed away, and so he never saw this. It was very hard to lose a colleague and inspiration, and actually a great colleague and a great mathematician and friend. So I comforted myself creating this whole series. I just kept crocheting. And so that is a series which is in memory of him. And so also that's what I made, like this series. And so this is a picture from another exhibit. And that is when I had with my good friend, I met Gail Rothschild, who is painting ancient linens and fabrics. And she's also has been painting like knitted structures without like even knitting, and we were always dreaming that we would like to have an exhibit together. So, well, we had it in Matatuk Museum, so we were just like very happy. And so this one, this model, maybe itself it's not, but the picture itself, that when Mathematics Institute in Cambridge was celebrating their 50th anniversary, they were publishing a book, 50 Visions of Mathematics. And so I was proud. I'm proud that one of those 50 visions was this picture. So then I said, okay, so then I think I can take photos too, which goes somewhere. I do take photos myself of these works. And so that one was like, yes, that was one thing. I really liked it. And then there is like this installation, which I did in Riga, White Cloud, which you saw. On these, like this is some other pictures. So there was like interview in Finnish TV. That was like yours came. Well, often I have a questions. What's the use of it? Like what's the practical use? Yeah, so also I crocheted a hyperbolic skirt, sort of like, thought maybe I can start like a fashion line for mathematicians. Well, trust me, it's a lot of work, and even if I did this one with a very close to 1, it was 20/19, yeah, so that ratio. So this skirt, and it's done in linen because first was suggested to do it in a wool, that would be faster, but when I quickly calculated that would be a calculated weight, and the weight would be about like 15 extra kilos. And I thought, well, I have enough extra kilos, I don't need 15 more. So, and even in a linen, the weight of the skirt is 1.5 kilos. So I have to be careful wearing it because originally when I was wearing from that weight, it just started to slide down. So that would be extra addition to my talk. So, I avoid wearing during the talks. So there is other people who are now using this way of crocheting, and one is Gabrielle Meyer. Gabby she was my husband's graduate student, and she learned it when I was doing, and yeah, so she has more patience. She does big things. Then some people invite me and see what they are having practical uses. Yeah, so that Marie she's doing these hats, and she had a sale of the hats, so. And so then I was this spring, I was visiting Palermo, and then there is artist Simonetta Russotto, and she does her hats, and she has been in fashion magazines in Italy, and so they are adoring, they say, they really like to use. And so this is, I lost the name of a jeweler, but they sent me a present at making a brooch. And then I had a cooperation with Gisela Baumann, and so she was teaching in Princeton, and she was teaching also in Cornell, and we were just teaching crochet to architecture students for exploring space. And so I'm then making these spaces in 3D printings. So we have a paper. So I don't have it, but you can find this Donald Donahue. He was listening to my talk. His wife brought him to the talk I was giving in Dublin. He reluctantly came, but then the next morning he said, oh, well, I really liked your talk. And what? I came up with this melody. There is a hyperbolic guitar. It's on YouTube. You can just find it and play it. So it's, he was just trying with the sound. So then I came up with a book, wrote a book, and hopefully next year will be second edition, and I'm just getting more stuff for writing this book. And then interesting thing was that editor of the book, she didn't know how to crochet, but while editing the book, she learned how to crochet, made her own hyperbolic plane, and then she came up as an English major. She has a double major, English and mathematics, and then she came up with this, with a poem, Crocheted Hyperbolic Plane, and so well, just saying. So that some Romanian designer used it as a chair, but I was so these planes have been introducing me to many interesting people, and one of them was Raymond Smullyan, who passed away this time. And also the people who have been mathematicians and all in some ways and artists. And Raymond Smullyan was trained as a concert pianist. He was actually in Gilead. And he said, so he ran away from, I asked him, why didn't he play? Because he played beautifully. And so he said, well, they were not teaching mathematics in Gilead, so he ran away and he became a magician and logician and one of the Alonso Church's students. And so, well, and then here he actually played for me that I was giving a talk in Gathering for Gardner where all these famous mathematicians, and I was so nervous before my talk, and he said, oh, come on, and he played me that Beethoven sonata. So sometimes there are things so there is usually these, some mathematicians
turn to the artists, but then there are artists who turn mathematicians. If you know from calculus the Taylor series, yeah, so he was an artist before. He was trained artist, and after that he became so then Samuel Morse, he was a painter. That's his painting actually on the left. Yeah, and then he went on to invent a telegraph. Robert Fulton, who created so he was also an artist before he went on to become an engineer and constructed steamboat and I guess first submarine too. Michael Friedman, who earned the Fields Medal in mathematics in 1986, he had said that until the age of 16, he couldn't decide whether he wants to be a painter or he wants to do mathematics. So he was like a really, and she essentially dropped mathematics and became like, she's one of the first ones who did 3D printing. And so it was quite successful, and then she said she can fully, follow mathematics, but also her passion on 3D printings and printing these. And yeah, I don't know, I haven't met her now for some time, but so she's one of the first ones. And Robert Bosch became like a mathematician who also is known now like an artist, and he became like teaching his students traveling salesman problem, and he was thinking how to explain for students what this problem is. And that's how he came up with these intricate, like space-filling curves in different waves. It's actually interesting works. And then doing like these is, so these crochet planes have got me to various places. Like for example, I was in this institute with Henri Poincaré, and these are the models you have to, yeah. So and then looking at the Man Ray, and then I worked with some. Yes, and then learning about like an artists who were inspired by the fourth dimensions and non-Euclidean geometry, and then like going again and well, what else are connections, and doing researches is I like this found this Russian poet who is one of these 20th century early 20th century inspired artists. I found it interesting, like his connection with like comparing poetry with like Euclidean and non-Euclidean geometries. But so, and I was asking humanities professor recently, who is on Russian literature, and he says no, he's quite unique. He didn't much inspired in the literature, but he did inspire in others. Like one of his followers was L. Lisitsky. And then investigating L. Lisitsky, I found his connections with Riga. And then you just like, so, start interesting one thing, and then it leads you to some other thing. Like there were three brothers, Pevsners, Anton, Alexei. And then the third one decided that he is not going to be Pevsner, but he became Naum Gabo. And so, well, and then they said that art is, so that, art must be inspiration controlled by mathematics. So well, and then their works, and math teachers turn into like a textiles too. And just one example is Ada Dietz. So she was a mathematics teacher. When she retired, she decided that she can use polynomial equations to describe how to do patterns in textiles and in weaving. And so that's quite a long time ago, but there is some interest in that. And making these designs, you can just like, if you like to play with computers, this is another game. There is a Wolfram, when you go to Wolfram Alpha. So there is like a way, and then you can just input. And then they are putting like, according to these equations, they are putting out like these designs. And so that's what used in weaving. So and then I'm just like continue to look at this, like kind of like artists who use mathematics, and I'm not going to try to read this name. I tried like to train myself, but this is an Iranian artist, and she had last year she had an exhibit in Guggenheim, first time, like, and what I like is her use of these various symmetries, creating patterns and following like Iranian mosque designs. And then she just like changes her own way. But then I started to look at her biography, and apparently at some point she has been studying in Cornell too. And and you just like find these amazing connections. And then one of my favorite ones is like that Rusosava and her works. Yeah, so well, I wish I would, I had that patience, but her way of crocheting like a steel and like these wires, which she started to do in Japan detention camp after the war. So, like it's really, really, really amazing, and all these forms and just the way like it really exists, and so it's like the way. So, okay, thank you. I think I did my.
Sorry, I forgot to present myself in the beginning. I was exhausted. I'm coming from Okay. Any comments, questions to Daina?
Thank you for that.
It's on. Should be on.
Okay.
Thank you for the nice talk. I didn't really get what you meant by the equation. Why is the fractional to the power of x with these hyperbolic planes that we have?
So that exponential growth? Yeah, the exponential growth appears actually, there are distances in which I didn't go in there, like there's a distances which changes exponentially. Well, the easiest for me is why I was involving it in, is that it's a ratio how I'm increasing number of stitches. And the number of stitches are growing exponentially. Like for example, if I'm starting a row with 10 stitches at the beginning, and then, these are not the ones. Okay, here we go. See, this is the first row, yeah, between my fingers, this much. And then it just like starts growing exponentially, yeah? So, and then like the most you can see here, this is starting like from the center, like a very center. And that is like crochet, but instead of every previous stitch, 2 stitches are added. Yeah, so it means like the next row has twice as many, and so on. Yeah.
Why I got lost was you start a circle, and then if you just don't add anything, it goes up as a sphere, and so like just a little bit more and one wouldn't be enough to make hyperbolic, but if you start with a line, then of course just something that
No, this is it's easy. It's the easiest way. Yeah, it's easiest way is doing like in line. Yes.
okay, thank you.
Yes.
Okay. Any other questions, comments?
So this one is like, so I was mentioning that figure 8 knot. Do you know what that knot is? No. Well, so if you do climbing, if you do like any climbing, like figure 8 knot is the one which is not going to slip. Yeah. So this is like, that's the tightest. And actually, when you are combining like a two. Like when you are combining like a 2 threads, and then the usual thing you add, yeah, but then sometimes it slips out. If you do it figure 8, it's not going to slip. Yeah, well, unless you have a very, very slippery, but no. And then if you talk in a knot theory, yeah, so then any knot is like we usually sort of like a, okay, so here we go. Sorry, technical people. So this is a one way, yeah, so you do it one. And then that doing figure 8 is like you do it this way, yeah, so and that's how you get it, and it's not going to slip. For knot theory, you like those ends you tie together, yeah, so like for a knot theory, so those 2 ends, like it has to be closed curve, yeah. So anyway, so this is that figure 8 knot, and what I was crocheting is this green piece, yeah, so this green boundary, that's a figure 8 knot. And then the brown thing, which fills inside, so that is hyperbolic plane. Yeah, so that's a complementary space for a figure-8 knot. And that is one of the best-known results of William Thurston. Hallam and Ferguson made actually sculpture of it also. But the interesting thing is, you can also think about like this surface itself. Yeah? So it's one-sided. You are welcome to come and try. So because, you know, like if you go, it's like a Möbius band in some ways. Yeah. So this is only one-sided surface. So it means like it's non-orientable.
And may I ask something? You talked in the beginning about this dilemma of different identities, that to be an artist or to be a teacher or scientist or mathematics, and what is valued, what is accepted. How do you think it affected on your thinking, that having different kind of identities?
Before I became artist through hyperbolic planes, I was teaching mathematics. I was teaching mathematics also. The mathematics course is like called mathematical explorations for students who have to have, in order to get a bachelor's degree in Cornell, you have to have at least one. You have to have at least one math course. So, and I was getting like these art students, and you know, like the ones mostly some from literature, and essentially students who were very nice and bright students, but they were totally scared of mathematics. Okay, so well, and they would come, you know, like, okay, you know, they would really, okay, they will try to survive my course. And then I really, there was like a point, I wanted to know how do they feel. You know, like, well, okay, after the course, well, I changed their thinking, but I really wanted, again, how do they feel? So it means for me, it was try to, well, what would happen to me if I do the art? Because this is up to that point, you know, like up to the point I'm teaching in university, and I'm still living with that, you know, like I'm as far possible from art as, you know, I have been taught whole life, you know, like you can't be an artist. I said, well, what happens if I do the things where I am told that I am bad? You know, like really you can't do that. Okay, so I took watercolor lessons. And I took a watercolor lessons, and I started to do, and then the beginning was horrible. And that's exactly, I thought, like at the beginning I couldn't do a thing. Yeah, and I'm not just saying you like I did a great art. This is my only portrait I have done. That's of my husband. So well, but that's yeah. So okay. So but this is like what I was, and what I learned is the first like I really experienced what that inside horror is. I can't do it, but then slowly I learned that essentially the things is, you do need to know the technique. And then I thought like, okay, actually there were things I knew. First of all, a perspective I knew from geometry, how to do it. Yeah, composition. I did some photography and I had done, you know, like something about the composition. So what I didn't know to do like before I started, like, okay, I knew that like for watercolor you dilute paint with the water. Yeah, so. And I have done some, you know, like kids in school with a bat. But then finding out about the colors and the mixtures, and so I just realized I didn't know the technique. And that's when I was teaching my students. So essentially, you do need a technique, you know, like, and this is it. And we had last time I taught that course, we got a wonderful results. That's a course where they came. And last project, what they were doing was that they did with a mathematical, but from their perspective. And we had a wonderful presentations and like things. Yeah, so I think that it is worth to try doing like, and actually it should do something which, you know, you are not sure or you are told that you are bad. You know, like it's just enhances your experience. It doesn't make you like maybe a professional or.
Yeah, I think it was very much perhaps related your negative experiences from school, so that teachers are
Yeah.
more building borders than helping you to cross borders and open your thinking.
Yeah.
Okay. Any comments, points?
What are your next projects?
What's my next project? Actually, I did a project. Well, that is an interesting thing. I just finished one project. I don't have a picture to project here. But there is a so-called International Free-Form Fiber Guild, and from where people have written to me. And every year I have a challenges, but they give a topic, and then you somehow you interpret that. And for many years, like I have been following, and they are having very amazing works. And when I was like, okay, well, this year's challenge was nature, and I'm going to participate. Well, I made the project, and and really did that. And of course, the day before the deadline, I'm submitting, and apparently it appears that you shouldn't submit it through the Facebook group, which I thought that's what the group was. Apparently, there is some group in Yahoo, whatever it is, and I should have done through that. Okay, I didn't read the rules. My project wasn't accepted, but so well. I can show you on my cell phone the picture while I made it, but I said, oh, it's okay. I made a picture, it will be in my second edition. So that was my project I just finished. But yeah, and well, my next project is, as I'm saying, like right now I'm working on a second edition of my book, which means I have to add 20% more new material and redo some pictures, and so, like something, yeah. So that's my next project.
I was very inspired on your work with toxic grief, because it somehow expressed the idea that combining things, making phenomena visible, it can be different languages, but when you combine those languages or different ways of thinking, you can get something extra. And this quite deep, complex phenomena, you made it visible and in a very sensitive way.
Yeah, well, so the one of the part which is my project is that I'm right now for the second edition. I'm just looking on a thing which surprised myself, because I created these models purely 20 years ago for teaching, like teaching like geometry, and people have done amazing things. And what has happened, so there is like one of those, and they're just amazing. I was surprised myself too that now even one of these models appeared in the Theoretical Physics journal. And that is now about like quantum computing and the curvature, and then it's like it was written by one of the co-authors, there's Leonard Susskind, who was a good friend of Richard Feynman, and he's a director in Physics Institute in Stanford. And then we were communicating, and then he said, oh yeah, now this plane, it really explains something like also in a string theory, how there are like dimensions can be like, people get out of it. I had no idea myself, yeah, and then I'm just combining all these things and just like showing it, and I had some other people too, that it is important to show something visually, because then they say like, okay, I have, like in several cases been an occasion I show it and I said, oh, this looks like similar, this is exactly, so I should try this in hyperbolic geometry to describe whatever, like they are doing in biology, or there was like something in astronomy, and yeah, so.
Yeah. Okay. If there is no more questions or comments, thank you, Daina, so much.
Thank you.
Thank you